part of the buffers, which is starting the calculations. Now, buffer calculations are in some respects a whole lot easier, because what you're going to do is you're going to basically take the Ka and you're going to solve for the hydronium ion concentration. Then you take the negative log of both sides. Once you do that, you end up with what is called the Henderson-Hasselbalch equation, which is basically the one used for buffers. Okay? And the trick to the Henderson-Hasselbalch equation is when these two are equal, then A minus over HA comes out equal to 1. And so if you take the log of 1, it's 0. So at the midpoint of the buffer zone, your pH is going to equal your pKa. Okay? And if you remember back in lab when we did the aqueous reaction where you had the indicator with the multicolors and one color across the other color, we had absorbance over here and one did this and one did that, and you were supposed to know the pH here. This was where the pH is equal to the pKa, which tells you the Ka of the indicator. Okay, that's just a little side note, but this is the equation we're going to use. Now, this equation is also on the equation sheet, and so anytime you have a buffer, you're going to use it. Okay, so the Henderson-Hasselbalch is very important because the ratio of the conjugate to the acid determines the pH of the buffer. So when the ratio varies, the pH is going to vary. So if the base form is higher, then the pH will be higher. When the acid form is higher, then the pH will be lower. Whereas the magnitude of the amount you have is the buffer capacity. Remember, the more you have, the more it can counteract. Okay, and remember, when they're equal to each other, then the log of this concentration is 0, and the pH is equal to the pKa, which is, again, the midpoint of the buffer zone. And remember, when something is stated multiple times, it's usually very important. So the midpoint of the buffer zone is going to come back and haunt us. Okay, so let's work a problem. Now, the problem that you have on your web sheet has A, B, C, and D. So we're going to do A, B, C, and then D. So we're back to the original. So what we're going to do is we're going to do a lactic acid buffer. Now, in order to do the lactic acid buffer, there are several other things we need to do. So first and foremost, the Ka is equal to 1.4 times 10 to the minus 4th, which means your pKa, which is the midpoint of the buffer zone, is the negative log of the Ka. So it's going to come out to be 3.8539. Now, typically we keep pHs 2 units, but we're back to working problems, concentrations, amounts, etc. So we're going to keep it 4 places after the decimal place. Okay. All right. The buffer is prepared by adding the lactic acid and the sodium lactate. So this is the salt. So concentration of the I'm going to call this H-lac is going to be equal to the moles, which is 1.880 grams, and we need the molecular weight, so I have that. And the lactic acid is 90.078 grams per 1 mole. So that would give us 2.08708 moles. Now, we're looking for the molarity, but hold on a minute. We'll get to that in just a second. So the lactic acid comes from the salt. So we're going to call that lac minus. So that's equal to 195 grams. And erase that because that's nasty. 195 grams. And remember, it's the sodium salt. So even though we only need the conjugate, we're going to have the whole thing. So that's 112.07 grams per 1 mole. So here we get a whopping 1.73998 moles. So keep it simple, 1.740 moles. Okay, so we're at moles. Don't we need molarity? Because remember, molarity is equal to moles per liter. Okay, now, so we're going to look at moles of HA, which is moles of HA over the total volume, right? Molarity of the conjugate is equal to moles of the conjugate over, again, the volume. So if you ratio these and you get the molarity of A minus over the molarity of HA, and you flip them because that's what's in the Henderson-Hasselbalch equation. So then what you end up with is the moles of A minus over liters divided by moles of HA over liters. Well, the liters are the same. So the net effect, and this only works for the Henderson-Hasselbalch equation, but it makes your life a whole lot easier. All you have to know is the moles. Okay? So if we go back to our Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the conjugate, in this case, lac minus, over H lac. So we know it's 3.8539 plus the log of 1.740 divided by 2.08708, which when you ratio these two, gives you a ratio of 0.83369 is my ratio. So if you take the log of that, 3.8539, and remember, if you don't go ahead and do the ratio and you put it in your calculator is going to work on order of operation. So unless you put the conjugate and the acid in parentheses, it's going to take the first one but not the second one in the log. Plus a negative 0.078995, which comes out equal to 3.7749, which means my pH is 3.77. Now notice, and we can record that up here or down, doesn't matter. Now notice that the midpoint of our buffer zone is slightly higher than what we ended up with. And this makes perfect sense if you think about it, because when you look at the moles, you have more acid than you do base. Therefore, your pH should be slightly lower. Okay? So that was A and B. Let's move on to C. Now at C and D is where, we're going to add strong acid in the first one, strong base in the second one. Okay? Now, we're starting with the previous species, so we're not changing any values. But remember back to the previous section, if we have an acid, the acid is going to react with the base form to produce the weak acid back. That's the net effect. And it is a reaction, so we're going to use a reaction equation. So we're going to have the H plus. It's going to react with the lac minus to produce H lac. Well, if I could spell, life would be good. Okay, so that's H-lac. Now, if you notice, this is not an equilibrium. It still goes back to the equilibrium because we're using the H-lac and the lac. But now we're going to vary the amounts. So what we do is we start with the amount we have. So for the lac, we're going to have 98. We had that before. 9983. And, whoops, put it in the wrong part. Let's do this again. 1.73998. The H-lac we had 2.08708. Now, the only thing we're missing is the H plus. Okay? So, remember, this is volume and this is molarity. So, moles is going to be equal to the volume times the molarity. Okay? So, our strong acid, which is H plus, is going to be equal to 0.0548 liters times 4.80 moles, which means that it is equal to 0.26304 moles. All right, so in this case, everything else is in moles, so we're going to keep it in moles. So initially, we're going to start with 0.26304. Now, this is a one-way reaction. This is not an equilibrium. So this isn't an ICE table. This is just a reaction. So what's going to happen is you're going to lose all of the H plus as it reacts with the lac minus, and it's going to be gained on the opposite side. 0.04. So net effect is that should drop out. If you get a value for that, you've done something wrong. So we end up with 1.47694 here and 2.35012. Now, guess what? We're back to the Henderson-Hasselbalch equation is equal to pKa plus the log of, is still lac minus, over H-lac. So when we do this, again, we have the 3.8539 because the pKa didn't change. And this is a separate problem from B. So we are going to end up with a separate pH. So we've got the log of the lac, which is 1.47694 divided by 2.35012. And again, I like to ratio that, and the ratio is 0.62845. So we end up with 3.8539 plus a negative 0.20172, which means it's 3.65218. So the pH, once you've added this acid, is 3.65. Okay? So, if you'll notice from B, we started with the midpoint of the buffer zone is 3.85. The conditions we started with were 3.7, so it was slightly less acidic. Sorry, wrong direction. And then once we added more acid, it became more acidic because acid was added. Strong acid was added. Okay, which makes perfect sense. So when you work these problems, think about, did this make sense? Okay, that brings us to D, which is the exact same thing. We're going back to the original buffer, but in this time, we're going to add a base instead of an acid. Okay, so we're going to add the strong base is going to react with the acid form, in this case the weak acid, to produce the conjugate base. Same as before. So in this case, we're going to be adding sodium hydroxide, so it's hydroxide plus H-lac produces lac minus. Now, again, we're back to the original. So initially, for the H-lac, we're back to 2.08708, what we started with, and this is 1.73998. Now, again, we need the moles of sodium hydroxide, which is the sodium hydroxide, and the sodium drops out, so we're not concerned with that. So that's going to be 0.0482 liters times 7.60 molar. So that's going to give us a whopping 0.36632. And again, keep 4 places non-zero after behind the decimal and you're fine. I tend to be a little OCD. So 0.36632. Again, this is a reaction. It is a one-way reaction. It is an equilibrium, so it's not an ICE table. It's just simple stoichiometry. And the beauty of acid-base reactions is it's only one mole at a time, so everything is 1 to 1. 1 mole of protons. So again, the strong base should drop totally out. If it doesn't, then you have a problem. So you're 1.72076, and now you're up to 2.1063. Again, Henderson-Hesse-Bach, pKa, plus the log of the lac minus over H-lac. Okay, so again, 3.8539 plus the log of, in this case, 2.1063 over 1.72076. The ratio here now is 1.22405 because you've increased the base. So if you're thinking about this, the pH should increase because pH is more basic at higher pH units. So that's 3.8539 plus 0.0877999. So that gives us 3.9416 and a bunch of 9s. So our pH for this one is 3.94. So if you notice, we started with, I think, 3.85, went down to like 3.77. The previous one went down a little bit farther, but this one, based upon the original, which is like 3.7, is higher. Again, we haven't killed the buffer because we're only 1 pH unit off, but we added strong base. So the net effect is we raise the pH, but still within buffer zone. Now, if killing the buffer is something different, and we'll get to that in a few minutes, but right now we're going to work with another one. Okay, so on this one, the question is what volume of HF must be added to prepare a buffer of a pH? Okay, well, first things first, we need our Ka value, which is 6.6 times 10 to the minus 4. And so our pKa of that value is 3.1805. Okay, because remember the pKa is the negative log of the Ka. All right, so what volume must be added to 750 milliliters of the salt? Okay, so this is the acid, weak acid, and this is your salt. So, again, pH is equal to pKa plus the log of this case, F minus, over HF. And we plug in what we know. We know we need a pH of 3.95. where pKa is 3.1805, and we're doing the log of the F minus over the HF. Now, here's the problem. We cannot use the molar concentration of the HF. We have to deal with this in moles because we will be adding a solution, so the molarity will change. But the moles do not change. So what we need is moles. So if we take 0.75 liters and multiply it by 0.5 molar, then we end up with 0.15 moles of our acid. So we're looking for X over 0.15. Oh, wait a minute. That was wrong. Because that we're not given, we're looking for this volume. So what we're given is this amount here, which is 0.75 liters times 0.2 molar, which is 0.15 moles of the F minus. So our F minus is the 0.15. When you're working these problems, it is really easy to get mixed up, so just make sure you know what it is you're dealing with. And so we're looking for the HF, so it gets an X. Okay, so we're going to do the math. We'll subtract from both sides and get 0.7695 is equal to the log of 0.15 divided by X. Now, side note, if you take 10 to the log of X, then that is equal to X. Mathematically, these are inverses. So what we're going to do is raise both sides to the 10th power, and that gives us 5.88166 is equal to 0.15 times X. So X is equal to 0.025503 moles. And this is moles of HF. And we were looking for volume, so we know that there are 0.5 moles of HF per 1 liter. So we get 0.051006 liters, or if you were asked for it in milliliters, you'd multiply it by 1,000, 0.006 milliliters of acid needs to be added to the solution. Okay, so in this particular case, if you're trying to make the buffer, you still worry about only the moles, but in this case you've got a solid and a volume, so you have to use the moles to find the volume needed to add. Now, here comes B, which is the minimal amount of hydroxide which will be needed to add to exceed the buffer capacity of the solution. So there are two ways to do this. Technically, if you exceed 1 unit, so if we're adding a base, it's going to increase the pH. So you would need a pH greater than 4.95 to kill the buffer. So you could do that. The easier thing is just totally kill it. So to totally kill it with a base is you eliminate all the acid form. Now, so from here we knew that we have 0.025503 moles of HF. Well, if the hydroxide reacts with the HF to produce only F minus, that's water, then we want to kill all of it. So what we're looking at is 1 mole of HF reacts with 1 mole of hydroxide. And we want the minimal amount, so let's go ahead and do grams, which means we need the molecular weight, which is 56.108 grams of KOH per 1 mole, KOH, and this the H. So we would need 1.4309 grams. That would totally kill the buffer. Now, if you wanted to do just enough, then you could go back and change the pH to 4.95 and then solve for the value. But it's simpler to just totally kill it. So here's working buffer problems. Now here's another one. This one is calculate the pH of a buffer containing pyruvic acid and sodium pyruvate. Okay, so on this one we need the Ka, and the Ka of pyruvic acid is given. So let's go ahead and do the pKa of pyruvic acid, which is 2.4949. Okay, and again, it's a Henderson-Hasselbalch equation is equal to pKa plus the log, in this case, of pyruvic ion and H pyruvic. So this will be H pyruvic, and this is PYR minus. And remember, these are strictly the acids and the conjugates. So we're given 2.4949 plus the log of, and in this case, we're given both values in molarity, but we don't know the volume. We know it's the same, but we don't know what it is. So let's just go ahead and use the values given. 0.06 molar over 0.05 molar. So when we look at this, the ratio is 1.2. So it's 2.4949 plus the log of 0.07918. Excuse me. That's the log value after we've taken the log of the 1.2. So we get 2.5740, which means the pH is 2.57 of this buffer solution. Okay. Now, one question that always comes up is, how do you know which buffer to pick? Well, that's actually a really simple question, assuming you have the chart. Now, I got the chart over here, but let's pretend we don't have the chart. So this is acetic acid, which has a Ka equal to 1.8 times 10 to the minus 5th. So the pKa is equal to 4.74. This is carbonic acid, which has a Ka equal to 1.4 times 10 to the minus 4. So the pKa is equal to 3.8539. And the lactic acid we just did a minute ago, but it's 4.4 times 10 to the minus 7. It's the Ka. So the pKa is equal to 6.36. And you can't read that. So 6.36. Okay, so we need a pH of 4. So basically we need to pick the one with the pKa closest to desired. So in this particular case, you look at these two, and the carbonic is only 0.2 off, so the H2CO3 is higher. Oh, wait, I reversed those. this is actually the carbonic, and this one here is the lactic acid. I knew it looked awful familiar. So in this case, it's going to be the lactic acid, because I mixed the values up. And if you look at your table, the lactic acid is 3.85, whereas the carbonic is 6.36. So you would consult a table of buffers to see which one would work the best. Okay. So in this particular case, we're going to work one more and look at the sodium acetate, the ratio needed. So in this, again, particular case, it's simply pH is equal to pKa plus the log of the acetate, which this is acetate, over the acetic acid is HAC. And in this particular case, we only want this ratio right here. This is our ratio. So remember, the Ka of acetic acid is 1.8 times 10 to the minus fifth. So the pKa is equal to 4.7447. So we need 4.68 is equal to 4.7447 plus the log of, and again, we're looking for the ratio, so this is x. So we end up with negative 0.0647 is equal to the log of the ratio. We're going to take base 10 to both sides, so we end up with the x, which is the ratio of acetate to acetic acid, is equal to 0.861589. Okay, so it's 0.8616 is the ratio. Okay, and sometimes that's all you're asked, and other times you're asked for more. Okay, so on this one, we've got a buffer, and it's prepared using phosphate and diphosphate and monophosphate. This is similar to the buffer we used in lab. And the question is will the buffer capacity be exceeded if 6.2 grams of potassium oxide are added, or potassium hydroxide are added to it? Okay, well, first thing we need is we're moving from 2 to 1. So this is the Ka2 value, which is 6.3 times 10 to the minus 8. So the pKa of this buffer is equal to 7.2007. Okay? So the question is we have this many moles of the acid and this many moles of the conjugate base. So remember, the base, a strong base, will react with the weak acid to produce the conjugate base. So the first question is how much potassium hydroxide do we have? We have 6.2 grams of KOH, and we know that it's 52.1056 grams of KOH per 1 mole. And remember that you're just splitting it up, so 1 mole of KOH produces 1 mole of OH minus, which means we end up with a whopping, let's see the value, 0.1108 moles. Again, this is a reaction. So we know that our OH minus is going to react with our acid form, which is H2PO4 minus, to produce HPO4 2 minus. So this is 0.1108. We know that we're given 0.25 and 0.150. So it subtracts 1108 minus 0.1108. And remember, this is just a stoichiometry reaction, so we don't have an ICE table. So this disappears. We're left with 0.1395 and 0.2605. Again, we're using the Henderson-Hasselbalch equation is equal to pKa plus the log, in this case, of HPO4 2 minus over H2PO4 minus. So your pH is going to be equal to 7.2007 plus the log of 0.2605 divided by 0.1395, which this ratio is 1.867. So if we continue over here, the pH is equal to 7.2007 plus 0.2711, which means my pH is going to be 7.4718 or 7.47, which we're still in the buffer zone. So the question is will the buffer capacity be exceeded? And the answer on this one is no. Okay. But on B, we're going to do the same thing. We're going to take 0.02 liters times 6 molar of the HCl to produce 0.12 moles of H+. Now, because this is B based upon A, let's go back and use the original amounts, which now H+ will react with the base form, which is HPO4 2 minus, yields the acid form. And since we've already done the math, it's 0.12. This one is 0.15. And this one is 0.25. So we're going to subtract it here and add it over here. So when we look at it, again, that should be empty. So it's 0.03. And it's 0.37. So if we were to run it, the pH is going to be equal to 7.2007 plus the log of 0.03 over 0.37. Now, if you look at this, before you even proceed any farther, you're like, wait, we have very little of the conjugate. So this is probably going to kill the buffer. So in this case, my ratio is 0.08108. So we get 7.2007 plus a negative 1.09. Now at this point, I absolutely know because I'm going to be beyond 1 pH unit. So it's 6.109. So the pH is 6.11, which is less than 1 pH unit off 7.2. So you're 6.1, at 6.2 you'd be okay, but you're not. So yes, we killed the buffer. And this is why if you're killing the buffer, it's really easy just to go ahead and drop 1 to 0. Then you know you're absolutely done. So we are just below the buffer zone on this one, so you can consider it dead. So we've completed the calculations in this section.